in math and chemistry from Arizona State University in 2015. He received his MS in 2018 from our department, and he's just finishing up his PhD this spring working with Professor Mitra. So your presentation today on one part of his thesis. But before I turn it over to him, I'll just mention that he's also won a number of awards, including the 3-minute thesis competition. He got the People's Choice Award for that last fall. He won the Vince Pizzito Statistical Computing Award last year, and also first place in an ASA section on imaging.
You listen. Carlos está dando una clase.
I don't know how to mute Julia. Can somebody do that? So if you're not muted, please mute yourself. Okay, so Carlos, I'm going to turn it over to you to give your talk, Reduced Rank Tensor on Tensor Regression and Tensor Variant ANOVA. The floor is yours.
Thank you very much, Dr. Meeker. Thank you for the introduction. Hello all, my name is Carlos. I'm a 6th-year candidate, and today I'm going to be talking about the first chapter of my thesis, Reduced Rank Tensor and Tensor Regression. And so, someone's not muted. So before talking about the regression model, first I'm going to motivate the model with a very interesting application, which is regarding suicide. Suicide is a very prevalent problem in the United States. It's the second leading cause of death for people under 35. And not only that, but it also accounts for 2/3 of all the homicides in the United States in 2017. Assessing suicide is very challenging, as nearly 80% who die of suicide deny suicide ideation in their last communication with a professional. With this in mind, just in 2017, provided a data set comprising of 17 young suicide who think of suicide, and 9 of whom have attempted suicide. Each one of these 17 subjects was exposed to 30 stimuli, word stimuli under the brain scanner, 10 of which are positive stimuli, 10 are negative stimuli, and 10 are death-related stimuli. And so all these stimuli from the 17 subjects was extracted from the MRI time series using the general linear model. The betas from this linear model is what we will use in our tensor response linear model here. And so this is just an overview of how I'm fitting to this data. The response here is a tensor, it's a 5th order tensor. And why is it a 5th order tensor? Well, because we have 3 kinds of stimuli, right? So one response is this row right here, which corresponds to all the brain imaging for one subject. We have 3 kinds of stimuli, positive, negative, and death-related stimuli. First mode of the 5th order tensor response. We also have 10 words for each type of word. So that is the second order, the second mode here. We also have 3 more that correspond to the spatial context, right? X, Y, and Z. And so those are of size 43, 56, and 20. On the other side, I have the sign matrix, and this is the same design matrix I would use in MANOVA. But I also have a tensor covariate that, because my response is a tensor, and the errors are also tensors. Now, I should mention that this right here is just MANOVA. So if I turn this observation y into a very long vector, this is just MANOVA. However, if I just fit MANOVA, there is a very existential problem here with MANOVA, and that is that this regression coefficient beta has an incredibly large number of parameters on it. And not only that, but the covariance that exists within each observation, that is, the between word types, within word types, and the spatial covariance that exist in these responses. It also has a very large number of parameters without any additional assumptions, more than 1 trillion parameters. And so MANOVA alone is not of 17 unless I introduce additional assumptions. And that is the goal of my talk. The goal of my talk is going to be how am I going to use a number of unconstrained parameters in this beta and in the covariance such that I'm able to fit this MANOVA model. I should mention that here it's a little unclear how I'm going to perform this product, right? This product right here is a product between a matrix and a tensor. So what is this, right? It's a tensor product, and that is going to be the link of my regression model, the X beta part, and so that is called a partial contraction. Before introducing the more general notion of partial contraction, first I'm going to look at some special cases. The first case is going to be the matrix vector product. And this matrix vector product, we'll learn it in high school. So essentially we have a matrix times a vector. These get canceled out, leaving us with just a vector. In Einstein notation here, what is happening is that these indices are being added up. So X is going to be fully contracted. The more general case is a tensor vector contraction, where the same thing is going to happen. So this index is going to be canceled with this index, leaving me with a 4x2 matrix. And that is going to, in Einstein notation, this K is just being added up to the coefficient. Similarly, the next more general case is the tensor matrix contraction. And again, the same thing is happening, except that now two indices are being canceled out, this one and this one. And again, in Einstein notation, what is happening is that I'm just adding up over these indices. The more general case of partial contraction is going to match this regression covariate with the regression coefficient x beta in the partial contraction. And similar to these cases, all of the indices of x are going to be canceled with all of the indices of beta, leaving me with the response size, which is the same size as the response here. And so that is the first ingredient of my regression coefficient. It's this x beta. The next ingredient in my regression model is going to be the errors, because this tensor response regression model is also going to have a tensor error. Before talking about the model for the tensor errors, let me first talk about reshapings. So if we look at this tensor right here, this is a 6th order tensor. It's 6th order. Why is it 6th order? Well, because it's a cube of cubes, right? So you can think of the first 3 indices here indicating the outer cubes, and the last 3 indices here indicating the inner cubes. And so this is one way of visualizing 6-dimensional objects. The goal here now is going to be how am I going to arrange these 2 to the power of 6 elements, right? There are 2 to the power of 6 elements in this supercube. One way I'm going to arrange them is using the vectorization. And the vectorization is just going to grab all of these 64 elements and grab them and put them in a very long vector. Another matricization is going to be the mode matricization. And the mode matricization is going to do the same, except that it's going to do it along one of the directions. So along this direction, I'm going to grab all of the elements, and I'm going to vectorize them along this direction, and also along this direction is going to do the same. And so in a way, this side is being matched to the rows and the rest to the columns. Another very important matricization is going to be the canonical matricization. Matricization grabs the first 3 indices and matches them in the rows, and the last 3 indices matching them to the columns. And so you can think of the rows matching the outer cube and the columns matching the inner cubes. And so these different notions of matricization are going to be very important later. And in particular, when I introduce the tensor very normal distribution, which is the distribution that I'm going to have in the errors. So here, this is the more general notion of normal. Here I say that a tensor follows a tensor very normal distribution if its vectorization follows a multivariate normal distribution. And the multivariate normal distribution has just the vectorized mean, but the covariance matrix is going to be a big Kronecker product of all of these scale matrices. I should mention that the first side here is going to be M1, so this is going to be an M1 by M1 correlation or covariance matrix, and this is going to be M of size MP, meaning that this last covariance matrix is going to be MP by MP. And so this right here, this covariance sigma, it's very massive, but this Kronecker product helps a lot. It helps first because, like I mentioned, it helps us split the correlation context into multiple covariance matrices. So this, if along one of the dimensions we have a spatial context, we could have some spatial correlation along this covariance matrix. If on the other hand I have a time series, I could have a time series correlation matrix along this context. So that is one practical reason for this Kronecker covariance. Another reason why this is so practical is parameter reduction, because this sigma, without any constraints, has a massive number of unconstrained parameters. But with this assumption of Kronecker separability, the number of parameters go down significantly. And I should mention that it even goes down further if I assume more correlation structures, because this could be AR1, for example, and that's just one parameter. This could be ARMA11, that's just two parameters. And so it's a very flexible model and practical model in that case. I should mention that this covariance has one identifiability issue, and that is here I could multiply this matrix sigma 1 by A as long as it's non-zero, and divide here by the same A, and the model will be unchanged. And so to deal with this identifiability, I need a way of proportionally constraining these covariance matrices. And the way I'm going to do it is by constraining the first element to be equal to 1, just like in any correlation matrix. So this sigma, which is the covariance of the errors, is now I know how to deal with the large number of parameters on it, but there's another place where this large overparameterization is happening, and this in the beta. And so how am I going to deal with the overparameterization in beta? I'm going to assume that it has some kind of simplifying format, some low-rank structure. In particular, I'm going to look at the Tucker format. This Tucker format, we say that this equality holds, meaning that this tensor B has a Tucker format if it can be expressed this way. And so meaning that there is this inner tensor, which we call the core tensor, that is of the same order of this. So this is a three-dimensional order, third order tensor, and this is the third order tensor too. So it's going to be of the same order, except now I'm going to have the stall matrices, and the stall matrices are going to be multiplied to each side of this core tensor, and these factor matrices that are told are going to also match the sizes of the larger tensor. So this side is going to match this side, and this side is going to match this side. And this is the notation that I use for the Tucker product, meaning that there is this core tensor and multiply to these three factor matrices. In this particular case here, I have a 15 by 15 by 15 tensor with more than 3,000 parameters there, or coefficients. But if I assume this low rank format, it just goes down to 240. And notice that here, when we talk about a rank, or what is a rank here, in the Tucker rank in particular is going to be the size of this core tensor, which in this case is 345. But this can change, and we will see later how we can. One special case, and one important special case of this format is going to be when this coefficient beta, when this core tensor has a super diagonal structure. It means that so along the super diagonal, and the super diagonal is just the places where the coefficients coincide. So this is position 111, this is position 222. 333 and 444. And so when this core tensor is arranged in that way, we have something called the CP format. And the CP format now forces the columns to have the same number of columns, forces the factor matrices to have the same number of columns, which in this case is 4. and that leads us to having a tensor B of more than 3,000 parameters only have 180 unconstrained parameters. And so recall that this rank, this CP rank, it can be chosen to be other numbers too. And again, we will see how these ranks can be chosen later. The last format that I'm going to talk about is going to be the tensor ring format. It has a different flavor. So here, what I have over here is a 4-dimensional tensor. Why is it a 4-dimensional tensor? You can think of it as a vector of cubes. And so that's what makes it a 4-dimensional tensor. And I'm going to say that it has a tensor ring format if it can be expressed this way. And so you can think of a matrix product going from A1 to A2. And so these two are canceled by this product. And similarly, this is canceled with this by this product, and this is canceled with this by this product. And you can see why it's called a tensor ring, right? It's all these 3-dimensional tensors arranged in a ring structure, leaving me with a tensor of size k, l, m, n, which is the size of my original tensor. The rank here is going to be the size of my products. So these products are going to be the rank. In this case, I chose it to be 2 to 2, 2, meaning that this tensor of 256 parameters only has 64 unconstrained parameters. And so these are different ways how I can deal with the over-parameterization that is present in this beta. The more general model here, now I can introduce it, is tensor and tensor regression, where the errors follow this tensor very normal distribution and the coefficient has some low rank format. This was proposed in 2014, This was first proposed in 2014 by Peter Hoff, and he proposed a format for the coefficient beta that we call the OP format. It's essentially just an outer product of matrices. We will see later, we will compare it to other formats later. In 2017, Eric Locke proposed this model where the sigmas are identity matrix. Essentially, there is no study of the covariance that exists within observations. And then there's also this model of Li and Zhang in 2017, where they look at vector-varied structure X's they look at the Tucker format on beta, and they have a very specific structure on this sigma. So it doesn't allow us to have other correlation structure like AR1 or ARMA or other. What we're going to propose is a unifying framework that puts all of these formats and all of these sigmas in the same framework. First, the Peter Hoff's model, we framed it in the context of tensor and tensor regression. Eric Locke's, we extended by modeling the errors, so these covariances. And then Li and Chang, we do the full Tucker format on this beta and allow for tensor covariance. And then we also propose the tensor ring format. Moreover, what we're interested in here is going to be inference. So how are we going to perform inference on this beta? And so that is also something that we do in this work. So I'm going to talk about maximum likelihood estimation. Recall only for the Tucker format. Recall this is my model. This is my tensor response, my tensor covariance, my tensor error, my regression coefficient, which now I'm going to assume has this Tucker format. And recall this is the Tucker format. We have a core tensor here, and then we have all of these factor matrices that are going to be multiplied to each one of the sides. Moreover, I'm going to have constraints here. The first constraints are going to be that these factor matrices are going to have this sort of generalized orthogonality of the columns. And it's going to be generalized. I said generalized because it's going to be with respect to these correlation matrices. And then I'm also going to have the assumption that I had before here, that the sigma ones are going to be constrained by having one element of one. I should mention that this constraint makes the model identifiable and along these directions, and it's also very practical. Like, it helps a lot with inference. The log likelihood of this model right here, I wrote it down here. for this sigma, this notation that I will use, sigma is just a Victor model. And the way I'm going to optimize the log likelihood is going to be through a block relaxation algorithm. So essentially, what I'm going to do is that I'm going to focus on only one of the parameters and optimize it while fixing the others, and then continue to the next one, and then keep doing that iteratively. In particular, I'm first going to estimate the L1s. So with some initial values, let's say I focus on L1, and then I estimate L1 by fixing all of the other L's and all of the M's and all of the sigmas. And then I go to the L2, and then I continue and I finish all the L's. Then I go to, for M1, I'm going to fix all of the L's. I'm going to fix all of the L's. I'm going to fix all of the M's that are not the first one, and fix all of the sigmas and estimate this M. And then I'm going to do the same with sigma and sigma squared. So sigma squared and sigma, they're going to be done at the same time. And that's going to be for fixed values of L, N, and the other sigmas. And I'm going to iterate all of these until I reach some convergence. First, this L1 right here, how do I estimate this L1? So this is my main focus on this slide. The way I'm going to estimate it is by expressing these regression, tensor and tensor regression. What I'm going to do is that I'm going to vectorize both sides. And when I vectorize both sides, now I can express it this way. And when I express it this way, what I have is, it's a type of multiple linear regression, where this L1 right here now is expressed here in terms of its vectorization. And I have this H matrix that is going to act like my covariates. This HI is going to involve my ith covariate and also all the fixed versions of all of the other coefficients in the Tucker product. And being a type of multiple linear regression, this is the estimate for this L1 is going to be just the generalized least squares. The next step is going to be profiling this beta. So remember the core tensor in the center. The way I'm going to optimize this is by I'm going to do the same thing I did before. I'm going to vectorize both sides of this regression. So that is shown here. And when I vectorize both sides, I get to see this beta is here. Recall this is the canonical matricization that we talked about, and this is just a transpose. And this looks terribly like a regression problem, doesn't it? And so, except that I have this M on the left. Now, it turns out this M is not really an issue because we have these constraints, right? That this is a big identity matrix. And so this is going to be very similar to just a multiple linear regression or a multivariate multiple linear regression problem. And so that is very practical. But what I'm going to do now is that I'm going to grab my estimate that I obtained, and I'm going to plug it back into the log likelihood, meaning that I'm going to profile this core tensor V. I'm going to profile it out of the log likelihood. And so if I do that, if I profile it out, and I express this profile log likelihood in terms only of M1, then I can express it like this. And this is just a Frobenius norm, where this Q matrix is going, it's a matrix that is going to involve all of the covariates. It's going to involve all of the sigmas except for the first one, all of the M's except for the first one, and it's going to involve all of the L's. And so now I need to do constraint optimization on this profile log likelihood. Constraint because I have this constraint right here. And so my constraint optimization here, it turns out that it has a very deep connection with the generalized singular value decomposition. Namely, if I perform the singular value decomposition, UDV transpose, on this matrix, recall this Q1 is a matrix that involves all of these parameters. By the way, anytime I see square roots here, I am always talking about the symmetric square root. And so if I perform the singular value of this matrix, then it turns out that the result for this constraint optimization is going to be this matrix right here. Now notice that this U right here is not the same U as this, right? And the reason this is like this is because this U right here is a square matrix, whereas this M is a tall matrix. Remember, these are the factor matrix in the Tucker product. And so the reason I have a star here is because I'm going to grab the leading decay columns of U. And so that is the result from this constraint optimization. And then I'm going to look at how to optimize the sigma 1 and sigma squared. And the way I do this is by expressing the log likelihood of this tensor variant normal model in this way. And so this looks very familiar, right? This is just the multivariate normal log likelihood. And so this S1 is like the sum of square errors in ANOVA. And if there wasn't any constraints, the estimate would just be 1 over n minus 1, S1, right? However, I have this constraint right here, so I need to perform also constraint optimization. And so it turns out that this constraint optimization is provided by Franz and Carvalho in 2018. And it's just this adjust procedure, which is a simple procedure and it's very, very intuitive too. And it turns out that once I've estimated this sigma 1, and I have this S1 from the estimation, sigma squared is given for free. So it's very cheap. It's just the trace of this. And this is just like a matrix in a product. So this is very cheap to do in R. And so that is very practical. This sigma squared is given to us from this adjust procedure as well. So now that I have all of these maximum likelihood estimators, I'm going to assemble my beta hats, my L hats, my M hats, and I'm going to have my coefficient beta hat. And this coefficient beta hat is going to have all of the maximum likelihood. And I'm also going to look at the counterpart, which is the population parameters. And I'm going to look at the sampling distribution. It turns out that my beta hat, my coefficient, my estimated coefficient, converges in distribution to a multivariate normal as the sample size goes to infinity. And this multivariate normal is asymptotically unbiased, I guess, here, and it has this sampling variance. Now, the outline for this proof is interesting. Recall that I said that the estimation of this core tensor is very similar to multiple linear regression, so it is just a linear transformation of Gaussian data, meaning that it is Gaussian itself, conditional on the other ones, on the other parameters. And so that is very practical. This is Gaussian, and that is not an approximation. It's going to be exactly Gaussian, and all of these estimates are consistent. So I'm going to assemble all of these right here, this Tucker product, using the multivariate Slatsky's theorem. And so this is how I get this result. There's also similar results for the CP format and the tensor ring format, but they're not going to use this Slatsky's theorem approach. They're going to use an approximation approach similar to the delta theorem. So let me talk about performance. First, I'm going to look at a two-factor ANOVA. And this two-factor ANOVA is going to be of matrices. So I'm going to be looking at matrix on matrix regression problem, where the two factors in my ANOVA are going to be 4 types of Andean camelids. I have an alpaca, a vicuña, a llama, and a guanaco. And then I also have the other factor is going to be the RGB color images. So my first factor has 4 levels, and my second factor has 3 levels, red, green, and blue. And my beta here, my beta coefficient is chosen such that it contains all of these color images of the Andean camelids. And so this beta right here is these 4 color images. And so I have k repetitions in a balanced design for each combination of factors. My covariance matrices here were chosen to be AR1. So this is AR1 of 87 by 87. This is AR1 of 106 and 106. These different models, right? We talked about different formats. In particular, I want you to look at these columns right here. Oh, I should mention that each column right here is one model. So all of these are the betas from one model. All of these are the betas from another model, and here are their BICs and their percent of parameter reduction. And so all of these 3 right here, CP set, Tucker set, TK is the Tucker, and the tensor ring set, I chose, the reason there is a subscript set there is because I chose the rank such that there is similar number of parameters in the tree, and also like a very small rank. And we look at that, these 3 look very blurry. And the reason is that the ranks of the Tucker CP or the tensor ring ranks, they were not, they were just chosen arbitrarily, right? But what I did is also, for each one of these three, I chose the rank using BIC. And so I approach the rank selection as a model selection problem. And when I do that, I have the CP optimal, I have the Tucker optimal rank, and I have the tensor ring optimal rank. And we can see that in these cases, the coefficient betas, the estimated coefficient betas, they look very similar to the original image. And so that is very practical, and it motivates these formats, because now we're able to choose the rank accordingly to the level of recovery that we want. I should mention also that this OP format, which is the Peter Hoff format from 2014, it has no rank. In a way, it is what it is, and it doesn't look visually appealing here. And in terms of VIC, it also performs the worst. And so the next I'm going to talk about a data application, the label fixes in the wild. And here we're going to do a 3-factor ANOVA. And my 3 factors are going to be continent of ethnic origin, 4 cohorts, so age groups, and 2 genders. And all of these attributes were taken from this research. I should mention that there are some problems with this data set, or not problems. So these labels, African, European, and Asian, I just chose them to be, I guess, politically correct, but the algorithms themselves and these attributes, they're not this. they have other names. And then I should also mention that this data set severely undersamples some combinations. Like, for example, senior Black women are severely undersampled compared to other. I'm going to use this data set only to show what tensor and tensor regression is doing, but with a caveat, right? Like, there's severe undersampling and so on. And so, like I said, we have this tensor and tensor. This is a 3-factor ANOVA. And when I say 3-factor ANOVA, in a way, I'm saying that this X is a 3-dimensional tensor. So essentially, there is a 1 at position ijk, indicating the 3 factors, the levels of the 3 factors. And my response is also going to be third order. It's going to be, because we have a color images, right? 151 by 111 by 3. So it's RGB color images. The sigma 1s were also chosen as AR1, and I chose this beta to be of the tensor ring format, and I chose it to be the tensor ring because of BIC. I optimized the ranks of the 3 formats that I proposed, and I chose the one that looks the best. And in terms of BIC, and this is the model that I proposed. I should say that this beta right here is all of this. All of this is that beta. So I'm showing this beta here. And in a way, we can see that this beta is showing us what we would expect from I guess visually what we think of this combination of factors. Like I said, this is just to illustrate what this tensor and tensor regression model is doing. There's no interest here of using this data set to do prediction or classification. However, I'm going to now talk about the motivating example that I originally was talking about. Here we have, remember, 5th order tensors as the response. Why 5th order? Well, because we have 3 types of words, and then we have 10 combinations of words for each type, and then we have spatial context, so X, Y, Z. And I am going to have vector covariates, and they're going to be vector because essentially we're just looking at the rows of this design matrix. And now I'm going to choose this beta right here. Remember, we had an issue with this beta, and the issue was that there was too many parameters here, over parameterization. And so I chose the Tucker format for this beta. And this Tucker format is going to reduce the number of parameters by more than 87%. And so I chose the ranks using BIC as well. And also the covariance here was chosen accordingly. So this sigma 1 indicates the correlation that exists between the 3 kinds of words. So it's a 3 by 3 matrix, and I left it unconstrained. The sigma 2 is going to look at the correlation within types of words. So it's 10 by 10, and I left that as equicorrelation of compound symmetry. And then these three right here are the spatial ones, and I'm going to leave them as AR1 to capture the spatial context of these brain images. Once I fit this model using my Tucker format, I also have the sampling distribution that I know from it. And recall that what I'm interested in is not this beta. What I'm interested in is in the interaction that exists between suicide attempt and death stimuli or word stimuli. And so how do I obtain this interaction from my estimated regression coefficient? The way I do it is the way we will do it in ANOVA, is using contrast matrices. And so we have a contrast matrix here that is going to find the difference between suicide attempters and suicide not attempters. We're going to have another interaction here that is going to be just a differencing matrix that is going to find all the differences along the three levels of the types of word stimuli. My third contrast here is just going to be an averaging contrast. I'm going to average out the 10 right here, which are just the 10 types of word stimuli, the 10 words within each type of word stimuli. And so this is really nice because now I'm able to use these products, these matrix products, with my regression coefficient beta to obtain an interaction term, beta star. And because I know its sampling distribution, I'm going to be able to standardize it. So my standardized interaction tensor is going to be, I'm going to call it Z hat. And this Z hat has all these nice properties that because it's standardized and because because of this result, it turns out that each one, that under the null hypothesis of no interaction at one particular voxel, my Z hat is going to approach the standard normal distribution. And so this Z hat contains all the Z statistics for the interactions on it. And these Z statistics are overlaid along brain images in this figure. Here I have the three levels of interaction. Recall that we have interactions along suicide attempters and suicide not attempters, but we also have an interaction between the three types of stimulus. So we have dead minus negative, dead minus positive, negative minus positive. First, when we look at the contrast that exists between dead stimuli and negative stimuli, we find significant activation in the precuneus. And this precuneus area is very important because this precuneus has been associated with depression and rumination. And so, moreover, when we look at the next level, which is the contrast between death and positive words, this activation in the precuneus is even more pronounced. And not only that, but we also have activation now in the dorsal and ventromedial prefrontal cortices, as well as in the mammillary bodies. And these areas are all involved in processing emotional information. What is interesting is that when we look at this, between negative and positive, so we're no longer looking at the death stimulus. Now we have very little interaction throughout. We have some interaction here in the temporal parietal junction that is associated with processing language, but overall we don't have as much activation in the brain. And so the conclusions that we get from this study is that negative and positive stimuli are more neurally similar when compared with the death stimulus. The death stimulus brings up regions of the brain that are associated with processing emotional information, decision making, and also yes. So I should mention that this study is only on a subset of 17 people. So by no means can this be generalized in general. But it shows that these tensor methods are very effective at allowing us to do inference and finding regions of the brain that are significantly activated. And it would be nice to have a really large data set, right? So this would be great if we had like people along different genders and races, and so that we could see what suicide looks like in the brain, and we could associate it with other neurological diseases that are out there. So in conclusion, I extended MANOVA for the tensor variance structure. So this MANOVA, I was able to fit this MANOVA model by having some additional structures on the MANOVA. Then I also have different tensor formats that allow me to perform this, and I compare all of these using BIC. I provided maximum likelihood estimation algorithms, their asymptotic properties. I didn't put them here, but I also provided, found like computational complexity of these algorithms. I also wrote an R package that I still haven't released it, but I'm still working on it. There's a lot of intricacies. And I evaluated my algorithms using simulations and data applications. In particular, I was able to distinguish facial characteristics using the LFW dataset. And I also was able to identify brain regions that are associated with suicide attempts and death-related stimuli. Finally, I would say that further work, remember at the very beginning, I talked about how I have a general linear model that extracted all these factors, all these betas from the MRI time series. And that's what I use in my tensor linear model. So instead of having this two-stage linear model, which is actually standard, people do that all the time, this two-stage linear model, we could also have like a tensor and tensor model that is time series integrated. And so this is another work that I'm working on. The main problem here is just computational. Like when you bring up the time series of brain images, it's just a massive problem. And so that is one of the things that I'm working on right now. Another chapter of my thesis looks at other types of distributions for tensors that are not just the tensor normal, and so that would really be helpful for like robust estimation methods for when the response are far from normal, from tensor varied normal. Of course, we would also like to do classification and prediction. We have some preliminary results that I didn't show here that are very promising. And so we would like, for example, to be able to classify whether someone is at risk of attempting suicide. And then finally, another way of doing this model is through mixed effects, right? So I could also do this model, this same MRI imaging model. I could also do it with the mixed effects model. The mixed effects comes from different subjects. And so this would be a different model that would also analyze the same data. And finally, we could extend these mixed effects models to gauge RNR for the cases where we have brain imaging coming from multiple imaging centers and along multiple subjects and multiple repetitions like test-retest data. And so this is very exciting too. This is also another of the works that I'm doing right now. And so, yeah, that is all that I have. Thank you.
Okay, thanks, Carlos. That was very interesting. So we'll open it up for questions now. If anybody has a question, I think you could either put it into the chat and I could read it, but I would also invite you just to unmute and ask your question. So I have a question, Carlos. In your algorithm to find the maximum likelihood estimates, as you described it, you are sequentially optimizing on one group of parameters, and then assuming all the others are fixed, and then you move to the next group. Is that algorithm something that you developed, or is that something well known? Does it have a name? And is there some theory that says that it's guaranteed to converge?
Right. So there is this interesting paper by Deliu in 1994 where he talks about these block relaxation algorithms and how they're used in statistics. And he developed some theory there too. Actually, he reviews some theory that has been developed for this. And so there is theory for it. And yeah, I would recommend this paper right here for these kinds of algorithms.
Does that, so block relaxation, that's the name of this method for finding the maximum likelihood estimates when you've got a large number of parameters? Okay.
Correct, yeah. And there's special cases of block relaxation that we use in statistics all the time, like the EM algorithm. So one can frame the EM algorithm in terms of block relaxation. And there are other algorithms too that can be framed in terms of block relaxation.
I see, okay. Okay, does anybody else have a question?
Yes, hi, Carlos. I have a question. I just find the idea of looking at images of a brain and essentially the images are indicating that the brain is pondering self-destruction, right? Like the brain is like hitting a button that is like auto destruct. And that just feels really striking to me, that you're able to look at the images of a brain deciding that it's going to shut down and die, maybe. So I don't know what that implies for you, or like the depth of this research for you.
Yeah, I never thought about it that way. But yes, that's in a way, it's kind of like the brain is ready to press the self-destruct button. Yeah, that's very interesting. Thank you.
Okay, I've got a chat question here, but I'll see if anybody. I see that Somak is unmuted. Do you have a question, Somak?
Yeah, that it was a very nice talk, Carlos. I have a very simple question. So, in regressions, we typically look at residuals or to kind of judge if the model was okay or do some diagnostics. Do you have any idea about how to do two things? The one is like model diagnostics, and the other one is goodness of fit.
Right, that is a really good question. I haven't explored doing model diagnostics using residuals. I think that is very important. I would say that I have been using BIC for most of these like model selection procedures, and so this in a way flexible Tucker models or tensor ring models, I am able to explore all the space of the rank using BIC, but yeah, it will be very interesting to look at residual approaches, especially considering that I'm assuming normality here. We have explored, I guess, with my advisor, we have been looking at ways of assessing normality, but assessing normality when the responses are really large it's very challenging. Like, for example, people do the energy test, but the energy test breaks down when P is smaller than the dimensions. But yes, I think that is further work, and that is also in a way what explore other types of assumptions on the errors, not just normality, but maybe like tensor T, or perhaps even like a robust method like a Tyler estimator. And so this is like a further work, but I agree. I think it'd be very interesting to find like diagnostic tools that uses the residuals. Yeah, we haven't done that. Yeah.
Cool. That's a great. Yeah, I think that's a great opportunity to do more things.
Yeah, I agree. Thank you for the comments.
Any others? Go ahead.
Hi, Carlos. So I have some questions for you. So you said that by asymptotic result of MLE, so you mean when the original model is Gaussian, right? So do you think that this kind of theory is still valid with non-Gaussian case?
That is an interesting question, yeah.
Because in the proof first, the outline of the proof, you said that new hat or something like that is already Gaussian. That can happen when the variables already are Gaussian. Right, assuming the response are Gaussian, yeah. Right. Yeah, it would be interesting to look at, for example, when we have like a robust estimation and what it looks like when the response is far from Gaussian, then this first assumption would not hold. But that is an interesting question. I'm guessing there's some kind of central limit theorem that is playing a role there. It would be interesting to study what it looks like. Okay. But I haven't studied that now. Like so far, I've been assuming normality, and then the next step would be to look at like robust or diagnostic methods, and also that would change all of this outline, right? So yeah, that is a very interesting question. There's further work how to find an asymptotic distribution for the cases where the responses are far from normal. Yeah. And also one more question. So you showed the images of different animals, right? Yes. So how's the performance of just pixel-wise regression? So is it possible to do a pixel-wise regression in this case? Right. So yeah, I can also do pixel-wise regression. that would be equivalent to just doing like simple linear regression, right? Like at each pixel.
Yeah.
Or multiple linear regression. The difference, I guess, is that doing that, I would be assuming that the sigmas are identity. So I'm disregarding in a way the correlation that exists within these voxels. Whereas here, I assume that they are AR1. And then the other thing is that if I just do like pixel-wise regression, then each one of these pixel-wise regressions is going to have a beta. And then collectively, all of these betas are just really massive, a really massive problem.
So the dimension is very high. That's true.
Right. So the dimension is very high, and so in a way, this allows me to not do pixel-wise regression, but to do everything integrated at once, and also be able to use the fact that this is a tensor to reduce the number of parameters with some low rank. But we have actually compared, and for all of these applications, we have compared these models with the model that you proposed, which is the pixel-wise regression, and at least in terms of BIC, it looks like we always beat it. So except for the OP, that was something very interesting that we found out. When we did pixel-wise regression, the pixel-wise regression, it actually beats this model, the OP. But in terms of BIC, even these still weren't as good. But all of these optimal ranks, the CP, the Tucker, and the tensor ring, they all beat the pixel-wise regression in terms of BIC at least.
And by the set, what do you mean by arbitrary rank? So you said that.
So again, in a way, it's not arbitrary. Actually, I chose it. I chose very specific ranks, and these ranks were essentially chosen here such that we have the same number of parameters roughly. So notice that here we have a 97.3% reduction. Here's a 97.4 and a 97.5. And so I just chose those ranks such that they are comparable, at least in terms of the dimensionality of the parameter space. But then I optimized these ranks using BIC to the three cases.
But if the ranks are similar, okay, sorry, there are too many questions. Other might have some questions. Sorry.
No, it's fine, but other people have questions too. That works.
And there is some. Oh, okay. Inference is not possible with pixel-wise regression. I see. Okay. So I will talk to you about this later. Sorry, no worries.
Thank you, Subrat.
Okay, so we have another chat question here. Let me read it. When it comes to image analysis, what are the pros and cons of tensor regression in comparison with deep learning architectures such as convolutional neural networks?
To be honest, I am not too familiar with like deep learning to answer this question. And I should say that deep learning, however, in convolutional neural networks, there's these layers. They also are learned using tensors, and so there is actually research to integrate the two. So there is, what is it called? Deep tensor networks, I think they're called. And so it's recent research that has like a tensor regression step within the neural network. But yeah, I should perhaps compare it against those.
Would it be an advantage that you have in your tensor regression model that perhaps the parameters are interpretable, whereas with deep learning they're not?
Right, that is a really good point. So essentially all I'm doing is MANOVA, right? And one of the key benefits of MANOVA is just that it's very interpretable. And so I know what is happening at every stage of the regression model. And so also inference is something that is very attractive with MANOVA. And so these are also good things for this model, that if you want to do inference, for example, if you want to find if you want to perform this analysis, and the way I obtain this Z statistic is just using elementary statistics, really. Like I'm doing what I would be doing in like statistics 501, for example, except that I'm doing it for tensors. But I'm using contrast matrices, and in a way, I am just extending what is already popular, right? What is like the linear model. I'm taking it like I'm trying to be able to generalize it for when the responses are tensors.
Okay,
And,
good.
yeah.
So Ranjan made a comment. His first comment was inference is not possible with pixel-wise regression. So this is in the chat. Ranjan, do you want to explain what you mean by? Could you elaborate on that just a little bit? Oh, your audio's off. Okay. So your microphone was very, very weak. I mean, I couldn't hear. I could tell that you were talking, but I couldn't make anything out. Okay, so Ranjan's had that
Are
problem.
we good?
Yeah, that's better.
Right. So, sorry. All I meant was that yes, we can fit individual models at a pixel or voxel, but then there has to be a way to combine them together, right? And that we don't really know. You have to bring in other assumptions, and that's why I don't. That's all I mean, actually.
Okay, I see. Yeah, and then I think the other point that you made is also important, that with deep learning you need a lot of data. 17 subjects would not be enough to do anything there, I guess. But I imagine many of these applications you might have a lot of data. So I was thinking, what would be the potential of using this model when you do have, let's say, a lot of subjects? Instead of just 17, that you've got some sort of a large study that was done that did that for maybe hundreds of individuals, and what we might learn from that. So it'd be interesting to maybe find somebody to collaborate with that could get access to that kind of data. Okay, so before we end, are there any final questions? Okay, so let's unmute and thank Carlos virtually for his very nice talk.
Thank you.
Thank you.
Okay.
Thank you.
Thanks, everybody.
Thank you.
Thank you.
Thank you.
Thank you.
Bye now.
Excellent.
So, Mac, did you have your hand up? Oh, you're just saying hi. Okay.
Very good.
Okay, bye, everybody.
Bye. Thank you.
Ciao.
Thanks, Bill.
Bye. Bien, Carlitos.